So in this video, we're going to take a look and overview of the history of astronomy. And if you're following along in the OpenStax textbook, that's chapters 2 and 3. So to give you an idea what we're going to do in this video, we're going to take a brief look at how the science of astronomy developed. We'll focus on the major players and how they made their discoveries. So the how is going to be very, very important for us because, of course, science requires proof and data. We'll also want to know, well, what can we learn about the planets and the stars and the universe in the process? So astronomy is really one of the earliest sciences, maybe the earliest, because all you need is your eyes to look up at the stars. But some ancient peoples tried to do a little bit better than just looking at the stars with their eyes. They actually built things that would help them see, okay, the stars and the sun are in this position at this time of year or this time of day. And very famously, we think that might be one thing that Stonehenge was used for. A lot of people also don't know there's other standing stones in Britain, but Stonehenge is certainly the most famous. And it may have been some kind of calendar for them. And the Mayans also had an observatory, and I believe it's called Chichen Itza in Central America. So ancient peoples were looking at the stars and absolutely were studying the astronomy. Certainly they needed it for sailing ships and things like that. The next few slides you're going to see have a blue background, and I did that on purpose. Because think about the blue of the oceans and the Earth. I mean, Earth is sometimes even called the blue planet. Because for the next few slides, we're going to be talking about the geocentric model. So think about the Earth as being the center of the universe. And a very important person with that was Aristotle, who lived roughly 300 BC. Now, Aristotle was right about a few things about the Earth. He gave us the idea that the Earth is round. And he knew this because he was able to observe eclipses. So with a lunar eclipse, he would see this round shape, and you can see that down here below. It's showing you the phases of the lunar eclipse as the moon gets darker and darker. And it often has a red color. And what was happening is this, the Earth is passing between the sun and the moon. So if here's the Earth, here's the sun, here's the moon, and he was getting a circular shadow. So because he was getting a circular shadow, because the sun's light rays are getting blocked by the Earth, he knew or surmised that the Earth has to be round. And he also knew that the stars are different at different points on the Earth. So if he was in Greece and he went further south to maybe somewhere in Africa, he would see different stars in the night sky. And he reasoned that, oh, well, as you travel on the Earth, you should see different stars because you're looking up at a different part of the sky. And what he got wrong was he said, well, then the Earth has to be at the center of the universe. The Earth is the center of all things. Now, he did have some reasoning for this. What he would say was, and notice, was, yeah, the stars do move in the night sky, but they don't move relative to each other. So one star doesn't race ahead of another star. They kind of move very, very evenly. So his idea, and I don't know if I can draw it real well here, is if we put the Earth at the center, that the stars were in some kind of sphere around it. And I think I don't think he called it this, but other people have described it as a crystal sphere. So you can imagine the Earth and then like a big glass globe encircling it. And on that glass globe, and it would be three-dimensional, like a glass ball, were all the stars. And they were what were rotating around the Earth. Now, and we're going to talk about that animation there at the bottom in a moment. But we want to jump ahead about 150 years to Ptolemy, who lived about 140 BC. He really supported Aristotle's idea. And what was important about Ptolemy was he was an excellent mathematician. And we'll see this theme again in just a little bit later in this slide. So if you look at Mars on the slide there, notice how Mars is going across the sky. There we go. See it going across the sky now? And Mars actually now backs up. you can see it was moving forward, and then it went backwards. Maybe I can even draw it on here. So if we looked at Mars, it went this way, and then kind of did a zigzag and went back. Aristotle really couldn't explain why this was, but Ptolemy could. Ptolemy did the math, and he said the planets are moving around the Earth in something called epicycles. Again, we still have a blue background here to indicate we're still geocentric with the Earth at the center of the universe. So epicycles put the Earth either at the center or roughly at the center. You can see it's a little off in this picture, but that's okay. And here's the planet. So if this were Mars, as Mars moves around the Earth, it also moves in this little epicycle. And I really like this picture over here because it shows, you could see, all right, there's the moon with its about 27-day cycle, and then all the cycles for the other planets, and even had the sun going around the Earth. So here's the Earth. He actually had the sun between Venus and Mars. And actually the math works. Now nowadays we'd probably update it with computers, but it's not that the math was totally wrong or that you can't describe the solar system that way. The question then becomes, well, is this really what's going on? Is the Earth truly at the center of the universe? And you're going to notice our background now went to a yellow color because now we're moving into the heliocentric model. And the heliocentric model, its first major proponent is Copernicus, and it's even called the Copernican revolution. Copernicus puts the sun at the center, and he does it, and he writes this book called On the Revolution of Celestial Orbs. He assumes circular orbits. That's not strictly true, and we'll see that in a few minutes, why that's not strictly true, but it's pretty close. And by doing this, he was able to get a much, much simpler mathematical model. It was much better for him mathematically to put the sun at the center and then think about Mercury and Venus. And you can even see that in the picture here. You can see Mercury, you can see Venus, Earth, Mardus is Mars. He had them, was using the Latin names. The problem was, Copernicus was right, but it took about 60 years to be accepted. And the problem wasn't so much the science or the math, it was the thinking. At the time of Copernicus, around 1500, Aristotle still reigns. And the idea is that Aristotle was working from pure reason. They had this idea that the universe could be understood solely by reasoning and logic and rhetoric. Empirical science really hadn't developed. The idea that it didn't really matter how elegant an idea was, what really matters is what data do you have. That philosophically hadn't quite developed yet. It was starting, but it wasn't quite there yet. Now, we're going to jump ahead a number of years. You see now we're in about 1564 to 1642 to Galileo. So we're maybe, to when Galileo's making these discoveries, maybe almost 100 years later. And now this idea that you have to have data, you have to back up your stuff, your claims with data is becoming accepted. A lot of that was due to a chemist by the name of Robert Boyle, who we won't discuss, but he was very big a proponent of what's called empiricism, the idea that science has to go where the data leads it. And a few things that Galileo did. Looking through his telescope, he was able to observe Jupiter's moons. And you can see that in the animation down below. And you could do this even with a fairly inexpensive telescope. You can see the moons of Jupiter. I've seen it through a very inexpensive department store kind of telescope. And what he found was, and he took records for a few months, was that he could see 4 very large moons. They're even called the Galilean moons in honor of him because he's the one who discovered it. And he found that these moons were revolving around Jupiter. So now we start to get to this idea that not everything has to revolve around the Earth. That things can go around bodies different than the Earth. So the idea that, well, the Earth goes around the sun isn't that unusual or that revolutionary anymore. He also, with his telescope, was able to get the phases of Venus. So we know that the moon goes through different phases. We have the full moons and the crescent moons and what's called the gibbous moon. But Venus does as well. We don't usually see it or probably notice it that often. But if you were looking with a telescope, you would. You'd see that Venus has the same idea where you get the crescent, just like you get a crescent moon. Gibbous is when you have part of a circle, or you can have a half of Venus. And the heliocentric model explained this much, much better. Those epicycles, they just couldn't explain it as well. And he also looked through his telescope and he saw mountains and craters on the moon. And they really looked a lot like the mountains on Earth, which suggested maybe Earth is just one of many bodies in the solar system. Maybe it's not so special that it has to be the center of the universe. And of course, we know that the church censored his ideas. However, the geocentrism idea was really out. The cat was out of the bag. With Galileo's observations, people more and more started to accept the idea of heliocentric, that the sun is at the center of the solar system. And another really huge name in astronomy is Kepler. And you can see he lives roughly the same time frame as Galileo. Kepler was not what we would maybe think of as a scientist. The scientist, we would think, well, that's the person who goes and looks through the telescope and gets the data. Well, the scientist in this case was a guy by the name of Tycho Brahe. Tycho was very, very, very wealthy. And telescopes in those days were very expensive. You couldn't go buy one at Christmas from Walmart. You couldn't go and order maybe a nicer one from Amazon or from a telescope website. They had to be handmade. The lenses were handmade. They had to be fitted and adjusted properly. Well, Tycho had the money. He had the money to have good telescopes, and he took 20 years of data. But Tycho wasn't really the great mathematician. He needed somebody to help him with the math. And that mathematician was Johannes Kepler. And Kepler, and he struggled with this because he was doing a lot of this math. He was doing it all by hand. No calculators, no computers. He's doing it all by hand. I mean, this took him quite a long time and even made a few errors that set him back a few months until he found it. You can imagine filling notebooks and notebooks and going through Brahe's 20 years of data to figure all this out. But he does. He refines Copernicus's circles. The circles were not perfect, so we had to make a little change on that, and Kepler was bright enough to be able to do the math. But really, really important, he was able to predict distances and the lengths of years with his math for all the planets that they knew of at that time in the solar system. That's another good point to make about science. Science really is, in a way, about telling the future. Now, not in the way that astrology says, oh, you're going to meet the love of your life or you're going to come into a lot of money. That's not what we mean. But Kepler's laws were able to predict, all right, if we see Mars here in the sky, where are we going to see Mars tomorrow? Where are we going to see Mars in 3 months or next year? So he's able, by mathematically, to predict where these things are going to be. So he makes an adjustment. Copernicus says circles, and that was a good start. But in reality, they're ellipses. Now, an ellipse is an oval. An oval doesn't have a precise mathematical definition, but an ellipse does. It has a formula. We won't get into the formula here. But what it means is that the orbits of the planets are ellipses, but the sun is at one focal point. Ellipses, a center always has, or a circle rather, just has a center, just the way we think about it. Now, we know where the center of a circle. But an ellipse has what we call 2 focal points. So you can imagine if I had a string and I pinned it down maybe with 2, push pins or thumbtacks or something, and I put a pencil here. As long as I kept my pencil on that string, I could go all the way around and I could draw this ellipse. So the sun is actually offset, and we don't go in a circle around it. Now, a reasonable question is, well, what's at this other focal point? Sometimes they're called foci. The answer is nothing. That's just empty space at that other focal point. So you can see really well on this animated diagram here how the planet goes in an ellipse, not a circle. Now, his second law says each planet sweeps out equal areas in equal times. And I believe on this one, it's into 12 things. So you see it goes a dark blue, then to that really light blue purple, and then to the dark one. And it makes about 12 slices. I believe that's the way it's set up. So the area of each of those slices, this area, and this area, I'll just do 2 in general. You'll see it'll pick it out again, are equal. Now, that's very mathematical, and maybe we would want to know, well, in everyday terms, what does that mean? In everyday terms, and maybe I'll get rid of those erasing on slide. There we go. I'll get rid of those circles. In more practical terms, what it means is that the Earth moves faster when it's closer to the sun. I think you can see it's way out far away from the sun, moving kind of slow. But then once it gets in close, it really whips around. And you can see in 1 month here, it goes quite a long distance. In 1 month out here, it's moving much slower. So we don't even move at the same speed around the sun. We move faster when we're closer. And Kepler figures this out in the 1600s. Now, the third law is a little bit scary. The good news is we're not going to do the math right now. But his third law, very powerful law, tells us that the length of a year for a planet is proportional to its distance from the sun. So the further away a planet is from the sun, the longer it will take to orbit. A really convenient unit to use is an astronomical unit, or an AU. So what's an AU? Well, what we define as an AU, and I'm not going to give you the exact number right now. 1 AU is the distance, average distance, between the sun and the Earth. And I say average because, as we said, it's an ellipse, so it's not going to be perfect. So it kind of makes sense. It's easy to talk about that. Venus is closer to the sun. It would be less than an AU. And it's not linear. The law is not linear. You can see squares and cubes, and as I said, we're not going to do the math right now. So the Earth is 1 AU from the sun, and we know it takes 1 year. That's how we define the length of our year. Mars is about 1.5 times as far, and you'll notice that the year is 1.88 years, so pretty close to 2 of our years. So it's not linear. It's about 1.5 times away, but closer to 2 times as long it takes to go around the sun. Jupiter is roughly 5 times the distance between the sun and the Earth, but its year is not 5, its year is 12. So it's increasing and increasing, and Pluto is about 40 times as far away from as the Earth is from the sun and takes 248 years. So just to give it kind of just one historical perspective, in the time that it takes the Earth to go around, well, that's 1 year. So for many of you, Jupiter has only gone around the sun maybe 1.5 or 2 times in your whole lifetime. For those of us who are a little bit older, like your humble narrator here, it's gone around a few more times. But, you know, if you're 24, 25 years old, in your whole lifetime, Jupiter's only gone around the sun twice. And Pluto, let's just use the United States as an example. Since the United States has been a country, Pluto hasn't really even gone around once. It's pretty close, 248 years, but that's where we are. Pluto moves very slow. It takes a long time because it's so far out. And Kepler figures this out. Now, Kepler didn't even know about Pluto, but the law still works. And of course, another really important person to mention is Isaac Newton. Isaac Newton, you know, a giant in the area of physics, comes up with the laws of motion, velocity, and acceleration, and talks about forces. So if you had a really good physics class in high school or college, you spent a lot of time with good old Newton. But the law that's really going to concern us here is the law of universal gravitation. Kepler knew that the planets went around the sun, but he didn't know why. He didn't know that gravity is the force. So if you can imagine taking a yo-yo and swinging it around, well, the string is the force that keeps the yo-yo going around in a circle. The force that keeps the Earth going around, the sun, is gravity. And Newton even improves on the math for Kepler, and his math was so good we can even use it for modern satellites. So a couple points here before we jump right into the law of universal gravitation is this difference between mass and weight. We often use them interchangeably. We say if something is very heavy, well, it's very massive, or it weighs a lot. And I know we do that in everyday colloquial conversation, but there is a difference scientifically. Mass is the amount of matter in an object. You can think of it as the number of atoms. It does not change. So if I have a certain mass on Earth, 50 to 60 kilograms, we'll go 55 kilograms, and I go into space, I'm still 55 kilograms. Mass is measured in kilograms because I haven't lost any atoms, assuming I didn't gain or lose any weight. But weight is the force caused by gravity. So we have weight. If we're standing on the Earth, I'll do a real simple picture here. We have weight because the Earth is pulling down on us. And it changes with distance. Gravity changes. So if you go in an airplane ride, wherever you're traveling to, you're further away from the center of the Earth. We always measure it from the center. We actually weigh a little bit less on an airplane. Now, if you brought a bathroom scale with you and tried to measure it, you wouldn't really be able to. It's such a small amount, you wouldn't really see any difference. But because you're further away, or I'm further away from the center of the Earth, we weigh less. Now, in metric, we use newtons for weight, but more commonly in the English or the imperial system, probably we're more used to working with pounds. So that's our weight. And here's the law of universal gravitation, and it looks really scary and intimidating. It says the force is equal to G. G is a gravitational constant. It's a really small number. Turns out gravity is actually a very weak force. It's the weakest of all the forces, of the four forces. And it's proportional to the mass of one object. So if it were the Earth, we might call that mass 1, and a person, we could call that mass 2. But the heavier the objects are, the greater the force, and it decreases with distance squared. Now think about how this works. The Earth has a strong pull on us, has a strong force of gravity. We know this. I'm sure as a child, or maybe even not, if you try to jump straight up in the air, you can't go that high. Neither can I. Maybe a foot or so, maybe a little more if you tuck your knees up. You can only jump so far into the air. So this is a very strong force because the mass of the Earth is massive. But if you stand next to a person, maybe you're standing in line to go into a movie or standing in line in a cafeteria, you don't feel a gravitational pull from that person. It's actually there. There actually is a gravitational pull because all objects are attracted to all other objects. But our masses are so small, let's say both people are 60 kilograms, that if we would run the numbers, it's really, really tiny. So that law of universal gravitation says everything in the universe is attracted to everything else. Jupiter's pulling on you and I right now. But Jupiter is so far away that the pull is almost nothing. But it's not technically zero, but it's so small we really couldn't measure it. And the distance also decreases with the distance squared. This is what we call an inverse square relationship. So let's see what that is. Let's say we're 1 meter away from each other. Now notice this r squared is in the bottom. We'll just say, well, the force is proportional to 1. I'm not going to put the newtons there because we'd have to get the mass and the g and all that. Now let's say let's say we're 1 meter from that person. Draw a little picture here. Now we're going to step 2 meters. We're going to separate ourselves a little bit. Well, now the force is proportional to 1 over 2 squared. Well, that's a fourth. So we're twice as far apart, but gravity's not half, gravity's a fourth. Similarly, if we stepped 3 meters apart, it would be proportional to 1 over 3 squared, or 1/9. So if we look at the force versus the separation, would drop off very, very quickly. So think about a rocket going into space. There was the SpaceX launch not all that long ago when I'm recording this video. As the astronauts moved away from the Earth, the force of gravity dropped faster and faster and faster. So this is a nice summary chart. And I'm not going to go through it because we kind of just did. But you can see how we go from the geocentric universe in the blue to the heliocentric universe in the yellow. And I think it tries to I think the chart does a good job summarizing what each of the different people brought to the table. And of course, astronomy and physics doesn't end with Newton. And this slide, I don't even hope to list all the important people who made their contributions, but just here's some that we will look at in future videos. We know that there are galaxies, and we know that the universe is expanding. Maybe you've even heard of this. And the person who brought that to the table was Edwin Hubble. And later, of course, the Hubble Space Telescope was named for him. So he's the one who figures out that the universe is expanding. And if the universe is expanding, well, that means it must have been much smaller at some point. And that was put forth by Father Lemaitre, who was actually a Catholic priest and an astronomer. And then George Gamow and 2 other fellows, Penzias and Wilson, did the experiments to say, yeah, the universe used to be really, really small, and it expanded in this Big Bang. And then, of course, as very, very important, right around the turn of the 20th century, we got some really good ideas. Well, the way we think about space and time may not be 100% correct. And that comes to us from Einstein, and a lot of the math was done by somebody by the name of Minkowski.